Hi scholars, today we're going to talk about a very important concept called average rate of change. This is a concept that is very useful in propelling you from high school mathematics onto undergraduate college mathematics. For example, we're going to use this idea and generalize this idea over the next few weeks to introduce the idea of the derivative, which is one of the most fundamental, beautiful, and important ideas that you'll probably see in your high school mathematical career. And it sort of is the gateway to calculus. Additionally, average rate of change is really useful in real-world modeling situations, and so we'll see a little of that as well. Okay, so first off, to motivate this, what is average rate of change and how is it different from slope? Okay, so remember when we were learning slope. So here's our xy plane, and when we were learning slope, we said, okay, let's draw ourselves a line, whatever, and let's say, what's the slope? And you said, okay, so slope was, right, here we'll do it in a different color, slope was change in y, right? Change in y over change in x, and so we define slope as change in y over change in x, right? And this is sort of how we did slope. And we drew many different lines, right? We could draw lines that had positive slopes, we could draw lines that had negative slopes, we could draw lines that had a slope of 0, right? Those would just be horizontal lines. And in either case, we use this definition of slope to sort of describe the lines, right? Is a really important characteristic of a linear function. Okay, so why do we need another concept, right? Called average rate of change. Well, here's y equals x squared, right? And if I asked you, what's the slope of y equals x squared? It's kind of a tricky question because a linear function has one slope. There's only one slope. You can calculate it. If you calculate it down here, it's the same as if you calculate it up here, right? The number, the steepness, doesn't change. In fact, that's what makes a line, because the steepness doesn't change no matter what 2 points you choose, right? Now, in y equals x squared, first off, there is no uniform steepness. It does not have a slope. However, we could say, it looks like between these 2 points, on average, the slope looks like that. And between these 2 points, on average, the slope looks like that. And over here, it looks like on average, the slope looks like this, right? And so we're not able to say that this function, this quadratic function, has one slope, but it does have a bunch of these different things that we could measure, right, between 2 points. That's what average rate of change is, okay? It's nothing more than slope, but slope measured on non-linear functions, on things like y equals x squared. Or we could have other functions like y equals x cubed that look like this, right? Or later on we'll learn about trigonometric functions, right? That go up and down, like y equals sine x and cosine x, right? So all of these, none of these functions have a slope, but at particular points, you could talk about what their slope is. At this point, you could talk about what its sort of average rate of change is, right? Or, between 2 points, right? So this is the big idea of this lesson. So let's take a look at a couple of examples. Example number 1. The function f of x is graphed to the right. Here it is. It looks like it's a quadratic function. Find the function's average rate of change, so here's the big idea of this video, on the interval -2 to +2. Okay, so this interval right here, when you're given an interval, we're talking about our x values, right? When x equals -2 into where x equals +2. So first off, let's find those points on this graph of f of x. So when x equals -2, right, there's x equals -2, I go down, and it looks like I have the point -2, -6, right? Appears to be on the graph. There it is. And when x equals +2, let me go over 1, 2, and I go up. Looks like I have the point here, 2, 2. Okay, so these are my 2 points. If I want to find out the average rate of change, this is another way of saying, what's the slope, right? Now I know that this is not a linear function, right? But we're saying if I were to draw a line between these 2 points, on average, right, how much is the function changing? Not at any one point, but on average, right? if you imagine from -2 to 2, right? We're just going along at a steady clip. You're at -2, you close your eyes. You open your eyes, you're at +2, 2, right? On average, what happened, right, over this time, this interval? And again, this is nothing more than slope. This is saying what is our delta y over our delta x, right? So we could write it that way. However, we're actually gonna, well, yeah, we can just reason about it this way. And later on, we'll do an example where we talk about a little more of the formal notation. So, okay, let's do it. So how does y change? Looks like delta y here changed by a unit of 8, right? Looks like change in x was 4. So change in x was 4. So I can say that the average rate of change between -2 to +2, that's how we would write that, is the same thing as 8 over 4, otherwise known as 2. So on average, over this interval, the y value increased by 2 units every time the x value increased by 1 unit. And it's as easy as that, right? We're able to find the slope of a nonlinear graph, the quote-unquote slope. We call it average rate of change. Okay, one more question. Is the function's average rate of change increasing or decreasing? Well, this is another way of asking, is the slope positive or negative, right? It's the same question. The average rate of change is increasing because here the slope is positive from -2 to 2, right? So the answer is it is increasing because the slope is positive. Now, if we'd asked between -6 and -4, for example, we say, okay, we could have also found, right, drawn a line, so a straight line to approximate between this point and this point. We could have calculated the slope. Well, there, yeah, it would have been decreasing, right? At this interval, at this portion of the graph, the function is decreasing. In this portion, it's increasing, right? At the vertex, it's actually 0, right? We could draw, sort of consider at the vertex here that the function is neither increasing nor decreasing at that one particular point, right? But it basically decreases, gets to 0, and then starts increasing. Okay, let's take a look at one more example. Example number 2. What is the rate of change of the function g of x equals x plus 1 over x between, on the interval, x equals 1 and x equals 3? Okay, so just really quickly, let's just review formally. We know that the slope, we defined it as change in y over change in x, which we could have written as like the y2 minus the y1, right? You remember this? Over x2 minus the x1. So this is how we sort of defined slope. This was slope. And we define average rate of change in a very similar way, only we can use function notation, okay? So average rate of change between 2 points, right? This is the slope between the point x1, y1 and x2, y2, right? The average rate of change between points that have x value of a and b, we can write that, let's use our g as our function, we can write that as g of b minus g of a over b minus a. And you think, oh man, this is a whole other formula I got to memorize, but I just really like my slope formula. This one I know, I've been doing it for years, but now I have to memorize another one. No. This is saying the exact same information, right? Y values, right? We're saying that there's a point, here we're saying there's a point x1, y1, right? On a graph, you can find the x value, y value of a point. And here we're saying that there's a point a, g of a, right? Which is saying that g of a is nothing more than the y value at the point when x equals a, right? This is the same information, all right? In the same way, my point x2, y2 is nothing more than the b and g of b, right? Right? So just as we can even do a quick sketch, right? If we wanted to sort of reason about this a little bit, right? We can say if this point right here is our first x value, right? And we can say that this point right here is our second x value. Well, if that point is a, then the function value over here, right, is certainly going to be f of a, and the function value over here is certainly going to be f of b, right? This is the same thing as y2, right, and x2, right? And so we say, what's the slope here? Which is, right, again, the average rate of change is nothing more than slope. We say, what's the slope of this line? You can reason that it's the same idea as slope. F of b minus f of a, change in y, over b minus a, right? Change in y over change in x. Okay, so very same idea. Okay, so now that we have this idea, we can actually just solve this problem without even graphing this function. It's an interesting function to try to graph, but we can do it just by sort of algebraically plugging things in. So let's do that pretty quickly. So we know that we want to find the average rate of change between the point 1 and 3, right? X equals 1, x equals 3. So this is going to be f of 3, or sorry, we'll call it, the function name is g. So let's say g of 3 minus g of 1 over 3 minus 1. Easy, right? Plug in, find the slope, right? Okay, so g of 3 is, if I plug in g of 3, it's 3 plus 1/3. Okay, so let's just write that out. That's fine. It's 3 plus 1/3 minus g of 1, which is 1 plus 1 over 1, which is 2, right? Minus 2, it's 1 plus 1, all over 3 minus 1, which is 2. We can keep going, so that's going to equal 3 minus 2 is just 1, so 1 plus 1/3 is 4/3, all over 2, okay? Which is the same thing as 4/6, which is the same thing as 2/3. So the average rate of change of this function between x equals 1 and x equals 3 is 2/3. Awesome.